talk about finding the resonant frequency in an aluminum 6061 cantilever beam. So hopefully people know from materials, aluminum 6061, Young's modulus 69 GPa. If it's a metal, my Poisson's ratio is 0.3, although we'll see if you have to utilize that in this lab or not. So the vibration of materials, we've talked about it a lot in class. We've done a ton of examples, either with vibrational modes of materials or our ECG or ECG curves or XRD, lots and lots of different, basically our sound, basically the notes, musical notes. Actually, I'm going to flip my screen here real quick. So musical notes. So we could use discrete Fourier transforms in order to kind of analyze all of these different kind of properties. So in this lab, what we're going to do is we are going to look at a cantilever beam. So some of the assumptions in a cantilever beam is that we are rigid. The beam is massless. So there are some assumptions in this cantilever beam equation that gives us this kind of natural frequency here that are going to be a little bit different from our real life scenario. Is our beam rigid, for example? No, it's elastic. We know that we're going to look at there's going to be some stress tensor associated to and some strain tensor, et cetera, et cetera. That's going to be associated with it. So this is an elastic material, so it is not rigid. Is it massless? No, there's some mass to this beam. Additionally, in this experiment, we place an accelerometer. So on this beam, we push down, deflect, and then we allow it to kind of, again, vibrate at a certain, and then we're going to figure out what is the kind of natural frequency or the resonant frequency, which is going to also correlate to our dominant frequency in our frequency spectrum. So when we see kind of the dominant frequency, that is going to correlate to this natural frequency or our resonant frequency. So you kind of have this equation that you've seen before, hopefully previously in our P-set. Again, E is the Young's modulus of our beam, I is the moment of inertia. So we should know that our moment of inertia equation, B times H cubed over 12 from mechanics of materials. So again, negligible mass, rigid rectangular cross section. So some of these are not going to be applicable. So when you're thinking about why, we're going to be calculating again, our seminal plot is going to be our frequency, and then you're going to have as a function of the length of our beam. So we're going to vary essentially the length of the beam here, and we're going to see the kind of experimental. So this is versus your. So we're going to see, okay, do these overlap? So if they don't overlap, some of these are some really nice ideas as to why they might not overlap. Also, maybe you want to kind of think about if there's aliasing and spectral leakage too in this experiment. So these are kind of the details of the experimental methods. Again, it's essentially the same that we've been kind of looking at previously. Make sure that basically you're being given a data set as usual in this lab. Make sure that these conditions are met. If not met, they're not met, still make sure that you're able to, again, avoid signal aliasing and spectral leakage. So double check on that data. So after that, you're going to, again, repeat this. We're going to measure the frequency, or we're going to measure essentially this graph, because we're going to get an output. Let me scroll down here. We're going to plot our accelerometer. Let's draw this again. So we're going to deflect our beam. That beam's going to deflect. The accelerometer here is going to kind of vibrate up and down. So we're going to get a plot of g acceleration versus time. So there's going to be some kind of frequency to this signal. We're going to then take that, do a Fourier transform, discrete Fourier transform on that signal, function frequency, get our frequency spectrum, and then we're going to then plot again, that seminal plot here. So these are some ideas of plots that you might want to include. So raw data, an example of kind of one curve denoting where is the dominant or natural frequency, and then you want, again, this frequency versus length, because we're going to be changing the length of this beam. So, and obviously you want to include a lot of the experimental details. So what is delta T? What is sub S? What is F Nyquist? What is my period? What is et cetera, et cetera. What is my delta T? What is my delta F? So all these kind of values. What is my big N, et cetera, et cetera, et cetera. So you want to go through and obviously define all that in your expression, and then of course calculate your total uncertainty, so which is going to include your bias x plus precision x squared square root, and of course if you're given an equation like this, there's lots of independent variables, so you're going to have to take some partial derivatives. So that's kind of the big high-level overview of what's going to be happening in this lab. And next time, in the next video, we're going to go into the actual experimental or the data analysis details. So I will see you in the next video. Thanks. Good one. Bye.